Hello friends, in this video we will cover the section 12.2. In this section we will define what is a vector, and also we will define the norm or the length of the vector and the addition and subtraction of vectors. The term vector is used by scientists to indicate a quantity such as displacement or velocity or force, in physics, that has both magnitude and direction. The vector can be defined by defining its magnitude and the direction. For instance, suppose a particle moves along a line segment from point A to another point B. We have a line segment or a line like this, and a particle moves from the point A to the point B. So the corresponding displacement vector V from the point A to point B will be like this. Shown in the figure also you can see a representation for a vector V from the point A and the point B, which is another representation. Has initial point A. The starting point is called the initial point of the vector V, and the terminal point B, which is called also the tip of the vector B, and we indicate this by writing V is equal to the vector from A to B in this form. So notice that the vector U from C to D has the same length and the same direction as the vector V, even though it is in a different position. Actually, we move the vector V to here, and we state actually we have the same vector, but the positions are different. But the position is not important here. We say that U and V are equivalent or equal, and we write U is equal to V because we define the vectors with two quantities, which are magnitude and direction. And the zero vector, denoted by bold 0, has length 0. Its length is equal to 0. For example, the length of the vector V is the distance actually if you consider the three-dimensional coordinate system from the point A to the point B. The zero vector is the only vector with no specific direction. There is no any direction for the zero vector, and it is the only vector with this property. So let's define the vector addition. Actually, from physics, U and V are vectors positioned so the initial point of V is at the terminal point of U. Then the sum U plus, denoted by U plus V, is the vector from the initial point of the vector U. This is the initial point of the vector U, and to the terminal point of the vector V. As you can see, the terminal point of the vector U is same as the initial point of the vector V. So by combining the initial point of the vector U and the terminal point of the vector V, which is the red vector, so this is the sum of the vectors U and V, U plus V, which is called the triangle law, since we obtain a triangle, you see. Or we can find the vector addition by the parallelogram law. Actually, it is obtained by sketching a parallelogram for the vectors U and V if we have the common initial point for the vectors U and V. Here, the initial point of the vector V is the terminal point of the vector U, but here the initial points are same. In this case, we use the parallelogram law to obtain the vector addition of the vectors U and V. Okay, as you can see, we have the commutativity property for the vector addition, namely U plus V is equal to V plus U. By moving the vector V to here, you can obtain U plus V, or by moving the vector U to here, you can obtain v plus u. This is the addition of v plus v and u. So from here we say u plus v. Okay, we have the same vector, which is the red one. Therefore v plus u is equal to u plus v. Visually, this is called the parallelogram law. And also we have another operation which is called scalar multiplication. If c is a scalar, namely a number, a real number, c is a real number, and v is a vector, then the scalar multiple we denoted by c times v. Actually, we apply the operation for a number times a vector. Okay, c times v, a vector c times v. So it is defined that the vector it is defined by the vector whose length is the absolute value of c times the length of the vector v, and whose direction is the same as v if c is a positive number or is opposite to v if it is a negative number. If c is equal to 0 or the vector is the 0 vector, so the scalar multiple will be equal to the 0 vector if one of them is 0. Okay, for example, we have a vector v here graphically. 2 times v will be in the same direction since the number 2 is a positive number, and its length will be equal to 2 times the length of the vector v. You see, the length of the vector v is 2 times v is bigger than v. Similarly, if you multiply the vector v by 1 over 2, so we obtain another vector in the same direction of the vector v, but its length is less than the vector v. Similarly, if you multiply the vector v by a negative number, the directions will be in the opposite side, you see. And the vector minus v, actually it is a scalar multiple of minus 1 and v, has the same length. You see, we have the same length because the absolute value of c is 1. 1 times the length of the vector v will be equal to the length of the vector v, but points in the opposite direction. So we call this vector the negative of the vector v, and the difference, namely the subtraction of two vectors denoted by u minus v, can be obtained by adding the vectors u and the negative of v. Okay, we have this common initial points for u and v. By taking the negative version of v, we have minus v here, you see, which is in the opposite side of the vector v, but the initial points are same. So u minus v will be, by using the parallelogram law, since we have the common initial point, we move minus v here, minus v. So u minus v, the order is important, u minus v will be this red vector, okay, u minus v. So if we place the initial point of a vector a at the origin of a rectangular coordinate system, we place a vector in two-dimensional coordinate system or three-dimensional coordinate system. So the terminal point of this vector has coordinates of the form a1, a2 or a1, a2, a3, depending on whether our coordinate system is two or three-dimensional. If we are in the two-dimensional coordinate system, so the number of components of a vector will be 2. If we are in the three-dimensional, so the number of components of the vector will be 3. You know, points are denoted in this form in the open parentheses, but vectors will be represented in this note as like this, in this form, okay? Not open parentheses. The symbols are used, written here, for representing a vector in two-dimensional and three-dimensional coordinate system. You see, the components of the vector A in two-dimensional and three-dimensionals is actually the components of the terminal point of this vector if its initial point is the origin, you see. Okay, so the vectors shown in this figure are all equivalent to the vector from the origin to the point P. Namely, we move the vector from the origin to the point P, which is the terminal point, to here, or this one. They are equal to the same vector, which is the vector from the origin to the point P in the two-dimensional coordinate system. All of them state the same vector actually, but the positions are different. So we choose a special one here, which is called the position vector of these vectors. And the position vector will be the vector from the origin to the point P. Namely, we choose always among them such that the initial point will be the origin. Okay. By moving this, we can obtain another representations by changing the position. Okay. But the real representation of them will be the vector whose initial point is the origin. So it is called the position vector of the point P. Okay. So in three dimensions, similarly, the vector from the origin to the point P is the position vector of the point P. Namely, for every point we obtain a position vector. For example, the point Q is here. So by sketching a line segment from the point Q to the origin, we obtain another position vector corresponding to point Q. So by moving, for example, the position vector of the point P, to here, we obtain the same vector, but the position is different. So for given points A and B, and they are the components of these points, so the vector A with representation A to B is equal to, namely we can find the components of the vector A if the initial point of this vector is A and the terminal point of the vector A is B. Can be, for example, like this. A is the initial point, B is the terminal point. Okay. So the components can be found by taking the difference of the components respectively. For the first component, we use the first components of the points x1 and x2. So since it is a vector from A to B, so we will apply the subtraction in this order. First we write the components of B, and then we write the components of the point A, since the initial point is A. If you write A minus B, the representation will be wrong for the vector A. Therefore, first you should write the terminal point of B, the vector A, which is B, minus, then you write the initial point. For example, let's find the vector represented by the directed line segment with initial point A and the terminal point B. So from here the vector corresponding to the representation from A to B, the initial point A and the terminal point B, you see we will apply B minus A, which is equal to minus 2, minus 2, minus 2. The second component is 1. First we write the component of B, 1, minus 3, 1, minus 4. And after necessary computation, the components of the vector are minus 4, 4, minus 3. And the magnitude or length of the vector V is the length of any of its representations. Namely, we have two vectors here, for example. Just by finding the length of one of them, we can find the other length for the other vector. Is denoted by the symbol in this form or like this. Also, we have another name for this quantity of the vector. It is called the norm. The norm of the vector V. Okay, we will say sometimes the magnitude of the vector V or the length of the vector V, or sometimes we say the norm of the vector V. So the length of two-dimensional vector A1, A2 is the square root of the addition of the squares of the components of the vector A. It is actually obtained for example in two-dimensional coordinate system, x-axis, y-axis. So the position vector will be the vector A has the components A1, A2, and this is actually the position vector of the point P, has the components A1, A2. So the distance from the origin to the point P, which is the terminal point of this vector, will be the length of the vector A. You know, the distance from the origin to here is A1, and the corresponding point on the y-axis is A2, which is the distance from the origin to the corresponding point on the y-axis, A2. And actually we have the same length for the vertical line here, A2, and we have actually a perpendicular triangle from here. So the distance from the origin to the terminal point of the vector A will be, by using the distance formula, you know, the length of the vector A will be equal to, from the Pythagorean theorem, the square root of A1 squared plus A2 squared. Okay, from here. Similarly, the length of three-dimensional vector will be the square root of the addition of the squares of the components of the vector A. And algebraically, the addition and the subtraction of two vectors can be easily found by adding the corresponding components. For two dimension, we have A1 plus B1, which is the addition of the first components, and the second component is the addition of the second components of the given vectors. We can say the same thing for three-dimensional vectors, you see. And the scalar multiplication can be found by multiplying each component by the scalar c, which is a real number, and we obtain algebraically the components of the scalar multiple of the vector v in this form. For example, we have two vectors a and b in three-dimensional coordinate system. Let's find the length of the vector a, which is easily found by using the formula. It is the square root of the squares of the components, you see, which is equal to 5, and the addition and subtraction of them, 3 times b and 2a plus 5b, which all of them can be found easily by using the definitions here. A plus b is the addition of the components, you see. A minus b is the difference of the components, you see. 3 times b is obtained by multiplying each component by the number 3, and 2a plus 5b can be found easily, by first applying the scalar multiplication for each one, and then applying the vector addition algebraically. So n-dimensional vector is an ordered n tuple. You can see we have n components generally, which is the most general form, in r to the power r to the n. Okay, it is a vector in n-dimensional rectangular coordinate system. We saw so far 2 dimensions and 3-dimensional coordinate system, but more generally we state n-dimensional space by assigning ordered n tuple for a point or a vector. Okay, we will see more information about n-dimensional vectors, especially in linear algebra next year. And we have some properties for operations between vectors. We have the commutativity property for the vector addition, and we have the associativity property. Namely, we can change the order of the parentheses for 2 vectors, since when we have addition of 3 vectors, and the addition of a vector by 0 vector, so we have itself, and the addition of a vector and its negative 1, so we will obtain the 0 vector. We can be easily proven, and the scalar can be distributed over the addition of 2 vectors, you see, and also the vector A can be distributed over the addition of numbers, you see, and so on. So in 3-dimensional coordinate system in R-cube, in 3-dimensional coordinate system, we have 3 special vectors which play a special role in applied science, in mathematics, and in useful concepts. For example, these are the vectors I, j, and k, bold I, bold j, and bold k. I is the vector 1, 0, 0, the second is 0, 1, 0, and the third one is 0, 0, 1. These vectors I, j, and k are called the standard basis vectors. Why do we say they are standard basis vectors? Because every vector can be written as a linear combination of them. I will show now in the next page. So they have length 1 and point in the directions of positive x, y, and z axis. Similarly, in 2 dimensions, we define I and j, 1, 0, and 0, 1. In 2-dimensional coordinate system, we have 2 special vectors. In 3 dimensions, we have 3 special vectors. 1, 0, 0 is corresponding to point on the x-axis. 0, 1, 0 is the terminal point of the vector j, and 0, 0, 1 is the terminal point of the vector k on the z-axis, and they are perpendicular to each other. Okay, and every vector, actually they are the codes of the axis of the 3-dimensional coordinate system. They are important because every vector you can select any arbitrary vector. The general representation will be in this form. So then we can write this as the addition of three vectors by writing A1 0 0, 0 A2 0 and 0 0 A3. And the first one is actually equal to the scalar multiple of the number A1 and the vector I, and similarly the second one is equal to the scalar multiplication here and this one. So you know 1 0 0 is the vector I, 0 1 0 is j, and 0 0 1 is the vector k. So every vector A in three-dimensional coordinate system, you see, is a linear combination of the vectors I, j, and k. Every vector can be represented by using these standard basis vectors. Therefore, they are important. And the vector A is actually the addition of three vectors, A1 times I, A2 times j, here, this one, A1 plus A2, and A3 times k, and plus A3 times k. Addition of three vectors, you know, by using the triangle or parallelogram law, which is actually the combination of the initial point of the first vector and the terminal point of the last one. Okay, and let's find an example. Let's solve an example about that. If we have two vectors represented by the standard basis vectors I plus 2j minus 3k, b is equal to 4i plus 7 times k, express the vector 2a plus 3b in terms of I, j, and k. So writing the definitions of the vectors I plus 2j minus 3k plus 3 times 4i plus 7k, and distributing the numbers into the parentheses, we obtain them, and applying the addition, we obtain 14i plus 4j plus 15k. Actually, another representation is written as 14, 4, and 50. Okay, we have two representations for vectors. This is the first one, another one is written here. So the unit vector is a vector whose length is equal to 1. For instance, the vectors, standard basis vectors I, j, and k are all unit vectors, because if you compute their lengths, which is the square root of the addition of the squares of the components, so you will obtain 1 for the length. Therefore, they are all unit vectors. In general, if we have a vector different from the zero vector in three-dimensional coordinate system, then the unit vector that has the same direction as the vector A can be found by applying the scalar multiplication for the number which is 1 over the length of the vector A and the vector A. This is the unit vector in the direction of the vector A. Okay, if you want to find the unit vector in the direction of the vector A, this is the vector A, for example, and the unit vector will be the vector U, which is in the same direction. The length is equal to 1 here, but the length of the vector A can be different from 1. So find the unit vector in the direction of the vector 2i minus j minus 2k. So the given vector has length if you apply the formula, which is the square root of the addition of the squares of the components. Here you see 2 squared plus minus 1 squared plus minus 2 squared, which is equal to 3. So by this equation the unit vector with the same direction like u, which is in the same direction of the vector a, is equal to 1 over the length of the vector a times the vector a, which is written as 1 over 3 times the vector a to I minus j minus 2k, and distributing the 1 over 3 into the parentheses, we obtain the components of the unit vector. If you compute the length of this vector, you will obtain 1. Therefore, this is the unit vector in the direction of this vector. 2 over 3 minus 1 over 3 minus 2 over 3. Okay, please find at your homes the written questions here, and when you have any question about that, please send your questions to my email. Thank you very much.